Look up at the night sky. Clear, dark night. The Milky Way appears. A faint milky band stretches across the heavens. That's our home. That's the Milky Way galaxy. For as long as we have been human, we have gazed at the stars and wondered, what is out there? Are we alone? Could we ever go there? Not just science fiction, a deep-seated human impulse. Let's start with some cosmic perspective. Our galaxy, the Milky Way, is big. Really big. It's a barred spiral galaxy, a majestic swirling collection of stars, gas, dust, dark matter. If you measured it across, you'd be looking at about 100,000 light-years. A light-year is the distance light travels in 1 year, about 6 trillion miles or 9.5 trillion kilometers. Estimates say between 100 billion and 400 billion stars. For every person on Earth, there are dozens of stars in our galaxy. Most of those stars have planets, exoplanets. That implies hundreds of billions, perhaps trillions of planets in the Milky Way. Why is Earth so good for life as we know it? It's because our planet has the perfect combination of ingredients, a recipe that is just right. Scientists call this the Goldilocks principle. First, there's our distance from the sun. We orbit within the habitable zone. Not too hot, not too cold for liquid water. Too close and water would boil away. Too far and water would freeze. Liquid water is the essential solvent for the chemistry of life. But it's not just about water. Earth has a substantial atmosphere that does several critical things for us. It provides the oxygen we breathe and creates pressure to keep water liquid. It also shields us from UV and burns up many meteoroids. Our magnetic field, produced by a molten iron core, deflects the solar wind and cosmic rays. Without it, solar wind would strip our atmosphere as it likely did on Mars. So, if we're going to venture out, where do we look? The most obvious places are right here: the Moon, Mars, the moons of the gas giants. No other planet is perfectly habitable, but some offer intriguing possibilities as outposts. Mars is at the top of the list, relatively close, and it once had liquid water and a thicker atmosphere. Now it's cold, dry, with a thin atmosphere, but not impossible. We can build pressurized habitats, extract water from ice, and grow food in greenhouses. Beyond Mars, the moons of the gas giants, Europa, Enceladus, Titan, are intriguing. Europa and Enceladus likely hide global saltwater oceans beneath thick ice shells, warmed by tidal heating. Surface conditions are lethal: intense radiation and extreme cold. Drilling or subsurface habitats would be necessary. Titan has a dense nitrogen atmosphere and lakes of methane, pressure similar to Earth but at frigid temperatures. Outside our system, exoplanets, super-Earths and Earth-like worlds are the targets for future exploration. So, how do we even find these distant worlds? We can't just see them directly. They're tiny, dim, and lost in their star's glare. One of the most successful techniques is the transit method, watching a star for tiny periodic dips in brightness. Missions like Kepler and TESS have been wildly successful, detecting thousands of candidates. From the dip depth, we estimate planet size. From the period, we get the orbital distance. As of 2025, we've confirmed over 5,000 exoplanets with many more candidates. TRAPPIST-1, about 40 light-years away, hosts 7 Earth-sized rocky planets. Several lie in its habitable zone. Proxima b, our nearest exoplanet at just over 4 light-years, is rocky and in its star's habitable zone. But red dwarfs flare violently. Their planets may be bathed in radiation, complicating habitability. Next-generation telescopes like JWST can do transit spectroscopy, analyzing starlight filtered through atmospheres. We search spectra for water vapor, oxygen, methane, carbon dioxide, chemical fingerprints that could indicate life. Finding biosignatures would be one of the most profound discoveries in human history. The universe is not a friendly place. Outside Earth's magnetic bubble, space is flooded with solar wind and galactic cosmic rays, high-energy particles. This radiation can tear DNA, increasing cancer risk, causing cataracts, and damaging the central nervous system. Sufficient shielding for multi-year journeys is a massive engineering challenge. Even a habitable zone exoplanet might have crushing gravity, toxic atmospheres, or lethal pressures and temperatures. Planets around red dwarfs may be tidally locked, permanent day and night hemispheres, with a narrow, stormy terminator band possibly habitable. Biology itself could be a threat. Unknown microbes might be pathogenic, and Earth microbes could be invasive. Extreme quarantine and astrobiology protocols are essential for any exploration or colonization. Even a footprint can carry enormous biological consequences. The single greatest obstacle to becoming an interstellar species is distance. Proxima Centauri, our nearest stellar neighbor, is over 4 light-years away, more than 25 trillion miles. Even our fastest probes would take thousands of years to reach nearby stars. Chemical rockets are not up to the task. Nuclear thermal rockets and nuclear pulse propulsion, Project Orion, could, in principle, cut travel to centuries rather than millennia. Light sails pushed by powerful lasers, breakthrough starshot, could send tiny probes to nearby stars in approximately 20 years. Scaling that technology for humans is vastly harder. Generational world ships, enormous self-sustaining habitats, are an option. Entire ecosystems aboard slow-moving vessels. These ships must have foolproof closed-loop life support, agriculture, water recycling, and energy for centuries. And they raise social questions. Is it fair to commit future generations to a voyage they didn't choose? Once we arrive, how do we live? It's unlikely we'll find a world where we can simply step out and breathe. Early colonists will create Earth-like bubbles, prefabricated, pressurized, shielded habitats assembled on site. Every breath, drop of water, and crumb of food must be produced, recycled, and monitored. Hydroponics, aeroponics, vertical farming, LED spectra tuned to photosynthesis will be core technologies. Protein may come from insects or lab-grown meat, efficient in mass, space, and resources. Long-term terraforming could change a planet's atmosphere, releasing greenhouse gases and engineered microbes to create oxygen over centuries. Alternately, O'Neill cylinders or Stanford Torrey could be built from asteroid materials, rotating habitats with artificial gravity and full ecosystems. Asteroid mining would provide raw materials to build habitats anywhere in space, oriented for optimal sunlight. Humanity's future might be not on planets but in custom-built worlds drifting among the stars, diverse, self-contained, and scalable. So, after this tour, what's the verdict? The answer is a qualified yes. It's possible, but the hardest thing we've ever done. We need revolutionary propulsion, foolproof life support, and effective radiation shielding, plus the ability to build self-sustaining habitats. In the near term, the Moon and Mars are our training grounds and shipyards for future interstellar ventures. A species confined to one planet is vulnerable to asteroid impacts, supervolcanoes, pandemics, or self-inflicted catastrophe. Spreading out is our ultimate insurance, a future where thousands of worlds host human civilizations.